Hello, everybody. Welcome to a little bit more magnetism. I'm going to go ahead and try to pick up where I left off last time. And we were talking about magnetic materials and uh, and magnetic domains. So let's talk a little bit more about um, what happens in a material. So we were here. What happens in a material with the idea that it can possibly be magnetized. So, essentially, just to kind of give you a very quick outline, I was talking about the idea that magnetism was a quantum mechanical effect to really be understood there. We can talk about there are basically three categories of magnetization in materials. So, oh, well, I don't really want that. Let's try and blank. There we go. Okay, so there are essentially three types of magnetism in materials, and they are, I mean, they're kind of easily described. So I figure we can do that and give you kind of an idea of um, what's prevalent and why. So first thing we have is ferromagnetism, say. This is very difficult to understand. It's the iron, right? Ferro. So it's the iron, it's the magnetism that's present in iron and those types of materials. Ferromagnetism. So this is a type of magnetism that can be locked in. It's not always. I mean, there are plenty of pieces of iron that are not magnets. But when you hold a magnet close to them, they can be magnetized. So this can be very strong and locked in. I'll say locked, because essentially what you've done, if you have a ferromagnet and you've made it a magnet, you have locked the domains. You go back up to this picture. You take the look at the second picture here, and you can see that these are randomized. So in order to get this to become a magnet, like in the top picture, then what you have to do is essentially ferromagnetism is an idea of how the atoms and the domains are locking together. So what you have to do is you have to um, get them kind of unlocked. Typically, you heat it, right, or you bang it with a hammer, and then you put a magnetic field. You put it in a magnetic field. You put it in a strong magnet, or you have right. You have the two poles of like a horseshoe magnet, and you stick this thing between them. And while it's hot, all of the domains line up with the external field, and then you cool it off and you lock them in, essentially, right? You cool it off while it's in the field, and then they all lock there, and then they become a magnet. So, and so ferromagnetism, it can be very a strong effect. It can also be, um, a, well, it can also be a situation where you have a material that's ferromagnetic, like iron, typical paperclip. It's not a magnet, but it will magnetize near a magnet. So what happens is there are kind of different levels of the strongness of the magnet of the ferromagnetism. So some ferromagnets you can put them near another magnet and their domains will line, and then you can take this magnet away and the domains will stay lined up for a little while, right? So this is the idea that perhaps you have a magnetic screwdriver or something like this, and then you hold this magnetic screwdriver near the screw, and then you take it away and the screw kind of is still a little bit sticky to like something else. um, and you say, oh, there's still a little bit of magnetism left in it, and there is. Other ones are very much more weakly coupled, wherein you say, oh, I have it near a magnet. I take the magnet away and it's gone. All right. So the strength of it kind of depends on how easily is it randomized And the randomization is typically due to thermal, right? The higher the temperature, the more crazy, weird motion is going on all over the place. And it's a competition between how much is the ferromagnetism trying to lock it and how much is the temperature of the thing trying to randomize it. So that's ferromagnetism. Essentially, paramagnetism, this is the one where it is not so ferromagnets are magnetic materials. All right, these are magnetic materials. These are, they can be magnetized. This is like the equivalent of induced polarization, like in a charge in an object that has that you know, like rub the balloon on your head and stick it on the wall. Well, the wall is not a conductor. It's not anything. It's just something where you can push charge around a little bit and the balloon will stick to the wall because of the responses of the charges in the wall. So ferromagnets are kind of like that. You can induce magnetization in them. And then when you take the thing away, everything's gone, right? When I take the balloon away from the wall doesn't stay kind of polarized. The charges don't stay where they are. They go back to where they were. So ferromagnets are kind of the same way. They can be magnetized, and yeah, and what do you want? I mean, there's a lot to say here. They can be magnetized. So paramagnetism is something in which you have a material, and it is not a magnet, and it never will be a magnet. It can't be a magnet like a ferromagnet can be a magnet. However, it can respond to magnetism. So if you take it and put it in an applied magnetic field, it will also line up and it will be slightly attracted, very slightly, weak, very weak. Okay. This is much weaker than ferromagnetism. Ferromagnetism is like a massive effect. It is long range order. Paramagnetism is weak compared to ferromagnetism. But it is an attractive effect between a material and a magnetic and a magnet. So it's kind of the same idea, right? As I take a paperclip and I slide a magnet really close to it, and all of a sudden the paperclip goes. Well, a paramagnet is basically the same thing. You take a magnet and you take something that's paramagnetic and you slide it close, and you got to get really close, and then it goes and it attracts. So it's an attraction between a magnet and an object and a material. Let's see, and the material. Okay. And then there's diamagnetism, which is exactly what you probably are thinking it might be. Also very weak. It is a repulsion between the magnet and the material. So why is magnetism happening? I'll go over this really quickly, but essentially, as I kind of had said before, you can break a magnet and you'll get two magnets, and that can go all the way down to the atoms. Okay, so at the atomic level, you have atoms. The atoms themselves are magnets. So the question is why? Well, like so many things, we have to look at the electrons. The electrons themselves are actually individual little magnets. And it's built in. It's so cool. So the magnets, the electrons have a magnetic field associated with them already, which is which is pretty amazing. So it's the electrons that really are the things. It's the electrons that really are the things that are little magnets. They have what's called a magnetic moment. And so you'd say, well, it's because of, charge that moves, and because the electron has a spin, it has a magnetic moment. Well, I was about to say that's true classically, and this is a classical class. So there you go. The electrons are little spinny things. Oh, this is classical. Oh, here's the atom. We're classical. I kind of got lost on that for a sec. Okay, so here's the nucleus of an atom. As always, a positive charge. And here's our classical atom. This is so bad. So why are you teaching it to us then? Because you're classical physicists right now. Look, here's the electron. It's whipping around like Earth in an orbit. As it revolves around the nucleus, just as Earth revolves around the sun, there's a orbital effect of charge in motion, which causes some magnetism from that. But the much bigger contribution is from the spin of the electron on its axis. So I'm going to draw a little arrow here, bing, just like that. Oh, you know what? I'm going to do it in red because magnets are always red. How about that? Bing, there we go. There's the magnetic moment of the electron. And this is so darn hard to understand from a classical sense. Anyway, so the electrons spin. So it's as if the electron, of course, the electron does not literally spin around like Earth does. It's simply a thing that we're ascribing to it as a characteristic. Nevertheless, it has a magnetic moment, and it's built in just like the charge is. And it just has it. So if you are paramagnetic, then typically you'll find that you have unpaired electrons in your shells. So you are, for example, almost everything, very strong paramagnetic effect in the alkali. Is it? No, what's that first row, first column right under hydrogen? Are those called the alkali metals or something like that? They all have the +1. So they have a reasonably good, though obviously very weak, paramagnetic effect. And the noble gases, which have filled shells, will typically not show a paramagnetic effect because they will be diamagnetic. Having no unpaired electrons means that they are going to show the diamagnetism. So essentially every material is paramagnetic and diamagnetic. It's just which one's a little bit more, they're competing effects, right? Which one's a bit more than the other one? Okay. I need to leave this, obviously. So we're going to move on. Let's go to magnetic forces. Well, actually, I'm not going to leave that. I guess I'll put in one last piece here, is that you can also create. So since I said charge in motion, I should write that down. Magnetism is essentially electric charge in motion. So that if you have an electrical current, you will see a magnetic effect from an electric current. And that was the thing that Faraday discovered. He thought, how can this be? There's a compass, and I turn the electricity on, and the compass goes frink, like that. And then he turns the electricity off, and the compass goes like that. And he says, how can this be? For several reasons. So magnetic forces. So let's talk about magnetic forces. We'll go back to the Lorentz force law here. we are going to finally deal with that other term. Okay, the force, this is an experimentally found law. So this is the charge of the thing, the electric field that the thing is in. And we've dealt with that. Now, if the thing is moving and it's in a magnetic field, well, now we've got to deal with this term. All right, so B is E and B are external fields. Okay, I'm just going to note that there is no self field. Some people have tried to solve the problem of the electron's effect of its own electric field on itself, and I think they may have gone crazy. I don't quite remember, but there's this idea of self action. Yeah, no. So E and B are external fields, and it's those that we're concerned about finding. Okay, but also we're concerned about the trajectory of a charge that we pass through these E and B fields, and this is what this is for. It's to find that trajectory of a charge. So Q is the charge and V is the velocity of the charge, and how that charge feels force when it's immersed in E and B fields is given by this. All right, so if we look at only the B field for now, so let's concentrate on the magnetic term now. We're gonna we've concentrated on the E term, so let's concentrate on the B term. For now. So F is equal to Q times V cross B. And are you all fairly familiar with the cross product? Also known as the vector product. This is a way to multiply two vectors that is not the dot product. So unlike the dot product, which is also known as the scalar product, the outcome of the dot product is a number. In other words, it tells you, for example, how much is this vector lying on top of that vector, right? So it gives you the overlap. Okay, how much overlap is there of this one onto that one? Okay. The scalar product. So you'd have something like this, vector A, you'll have something like this, vector B, and you'd ask, what is A dot B? And you say, well, if I look at this and I say, well, look at A, and I go down here and I say, oh, look, this is the projection of A onto B, right? So it's the multiplication of the projection of that vector with vector B. So it's AB times the cosine of the angle, right? And there's your angle there. Or if you're doing it with vector components, it would be the x components of each one multiplied together plus the y components of each one multiplied together, right? Like this, ax bx plus ay by. All right. So this is not that. Thanks a lot for spending this time talking about what this isn't. Oh, you're welcome. The vector product is a completely different animal. So the vector product is essentially, we'll go back to our good old vectors A and B again. The vector product is essentially the area of of a parallelogram. So when you do A cross B, what you get is essentially the area of this thing, and you get the direction of the area. And remember, the direction of the area is always normal to the area. So what that means is I have to get a vector that's pointing that way out of the plane of made by the plane of A and B. And so if I was going to have that, well, then I would not write A cross B if I was going to have that. So that I'm going to have to write B cross A if I do that. The direction of the final vector here, this would be the direction of B cross A. Sorry about that. The direction of A cross B would be this one. Same area, just negative direction. So how do you do this? Well, essentially, if you do it geometrically, as I did over here with the dot product, A dot B, and I look at, well, it's the overlap and the cosine. Here, what it is essentially, it's the magnitudes of each vector times the sine of the angle between them, which again could be that. And now if I look at that, A sine theta would be this thing right here, right? So multiplying that times B, you can see is the rectangular area. And that's that. So then if you say, oh, well, how is this a rectangular area? Well, you just added on this triangle, and then over here, oops, well, okay, we'll do it backwards. We'll do it the other way. Well, yeah, we'll do that. Okay, go back, get that thing out of there. Here, so actually, let me take that off. Let me take that off. Come on. Okay, let me do it this way. AB sine theta. So here is A sine theta here. And then it's like as if you multiplied A sine theta times B, which would have been this big, large rectangular area. But that means I included this full triangle over here on the right. And here's B. Okay, so it's like, then you just leave this part off. So those two are equivalent triangles. So the rectangle area is the same as the parallelogram area. Okay, so it's AB sine theta. Now that is going to be pretty much the way I want to work with it. It's a vector. I'm setting bad modeling here because when you have a vector, you have to include a direction. So I'm going to include the n hat direction, which is the normal to the surface that's made by A and B. So in this case, how do you determine the direction of this n hat vector? This is once again the unit normal to the surface. This is the same thing we saw in Gauss's law, E dot dA, right? dA what? dA n hat, right? So if it's the outward pointing, unit normal, outward pointing. Okay, but how do you find the directionality of this? Which way is outwards? This is a surface. Which way is out? Okay, in order to find that, you have to use what's called the right-hand rule. And those of you who know this are going, oh. And those of you who don't know this are going, oh, what? So the right-hand rule essentially defines the directionality of the A cross B direction. And I'll give you a couple of examples of how to think about it. It's inherently a three-dimensional situation. Okay, I have to have three mutually perpendicular vectors here. A and B, right? A sine theta is the perpendicular piece to B. So the plane that's formed by A sine theta and B is the plane of the area, and therefore the unit normal is at right angles to that, right? Called orthogonal. So which direction is it? Is it A cross B or B cross A? Well, in this case, it would follow the same thing as X and Y. If you know about the XY axes, there's also typically a Z axis, which comes out of the page at you like that. And how do you get that Z axis? Well, what you do is you take your right hand and you say, okay, this is the easiest way for me. There are at least 3 ways to do this. You put your fingers in the direction of the X, right like that, okay? And then I'm gonna curl them in the direction of the Y. And then you see my thumb, which is over here, is pointing at me. And that's the direction of the Z, right? Like this. I curl. So I go X, curl direction of Y, then thumb points Z. And that's how you do the cross product. So in the case above, A cross B, I would have put A, my fingers in the direction of A. Well, let's do it this way, A. And then I'm trying to curl them in the direction of B. Uh-oh, can't do that. Must turn fingers around so that I can, and then thumb would point the direction of A cross B, which is downwards. Okay, A cross B is downwards. So my way of doing the rule is essentially that the first term, fingers with the first term. Okay. Whatever is first in the cross product, fingers point with the first term. Then curl your fingers towards the next one, right? Just try to make them go in that direction. So it's not like I'm changing the rotation of my hand or anything. For example, this XY one here, I've got the X this way, and all I'm doing is trying to make the fingers go in the direction of Y, like that. And then Z, you can't see it, but Z would have been out at me like this. So X, and then just curl the Y and go like that. So curl fingers in the direction of the second thing. Thumb points the result. Okay. This is also, there's a situation with X and Y. This is also essentially the basis of the right hand screw threads, right? Righty tighty. Well, if you curl your fingers with the direction of the rotation of the screw threads, right? Suppose I'm driving a screw into a material. I'm going righty tighty, which means I'm curling clockwise, and then my thumb is pointing the direction of the travel of the screw. As I turn the screw, it goes that way, right? So that's essentially the same kind of thing here. Just don't work on non-drive side bottom brackets of bicycles. All right. So right hand screw threads are ones where you turn the screw clockwise, righty tighty, and then the screw goes in, and then you counterclockwise like this, and it comes that way out. So that is basically the right hand rule. Okay. So that being said, let's go ahead and give this a try. Let's give this a try. So let's suppose we do an example here. All right. So suppose that well, I guess the quickest and easiest thing to get started on is called the mass spectrometer. The mass spectrometer is an instrument that separates basically materials like ions based on their masses. Effectively, here's what it looks like. I am going to shoot in a large number of positively charged ions, right? So here's a positive charge, and it's going that way. And when it gets over here, it's going to encounter a magnetic field. Now, the magnetic field, I'm going to say, is pointed out of the page towards us. And how do I denote that? Well, that's a good question. So here's how I denote it, with a dot. So I have a magnetic field. So what you can think of here is that it's essentially as if you are the south pole of the magnet, and the north pole is on the other side of the screen here. And there's a magnetic field. Wait, what did I just say? The north pole is on the other side. So the magnetic field's coming out of the north pole and it's coming directly towards you this way. Whoa, wait, I guess I can do it this. It's going that way, which is opposite to what it's doing to me. Yeah, well. So here's the magnetic field that I want this charge to go into, and it's pointed outwards. So it's almost as if, like I said, it's almost as if it's between two poles of a horseshoe magnet. So let's see here, like that, and then you could think of okay, so here's your typical horseshoe magnet, and north to south would look like this. So imagine that you rotated it that way and then stuck the north behind and the south up. So the vectors are all fairly well represented in the direction of the plane of the board here, but we have to have a convention. So that's a vector pointing from left to right. Here's a vector pointing outwards. And here's a vector pointing inwards. Okay. The reason for that is if you look at the three-dimensional representation of this vector here, it actually doesn't look like that. It looks like this. So that if you were to go look at it from this side, then you would see a dot with a circle around it. I suppose. I typically don't bother drawing the circle. And then the other side would be an X with a circle around it. So there you go. I am typically just going to draw the dot. So the mass spectrometer, here comes this thing, and it comes flying into the magnetic field. And I'll just put one more row on top here just so that we have complete coverage of everything. So here comes the charged particle, whatever it is, and it hits the magnetic field. Okay, I need to label that B. Okay, and so we're going to practice our V cross B. All right, so V cross B is in which direction? Because it turns out that the force on the charged particle is going to be in that direction. So V cross B is in what direction? Take a minute now and see if you can figure this out. Well, if you said, you got to use your right hand. I highly suggest always sticking with the right hand, at least until you are totally comfortable with the right hand rule. Okay, don't start pulling left-hand rules. Okay, not the way to do it. Until you're comfortable. All right. So look, I've got a V going this way. All right, V going this way, and then I would curl. Excuse me. I would curl with the field, which in this case, as I'm looking at it, would have been this way. Therefore, my thumb is pointing downwards. Okay. Just practice that out and see if you can get that. So in this case, I've got right fingers with V, curl with B, which is out, and then thumb points. Oops, I'm holding this, and then thumb points downwards, right? So as it gets in here, what's going to happen? It's going to point downwards. And then as the velocity turns, okay, so then at some later point, the velocity it's gonna start turning like this. Then the velocity is kind of pointed this way. Well, now what happens? Well, now V is kind of down that way, and I'm pointing and I'm curling with the field. But look what happens. The force, right? If I go V and then curl with B, it's gonna always go like this. The force is going to be perpendicular, right? It's going to be perpendicular to the velocity. So the force is going to be pointed straight downwards. F is downwards, but over here, then it's going to be pointed this way. And then as it turns, it's going to turn more. And then over here, it's going to be pointed this way. And then it turns and turns and turns. And look at that, right? F. Now the velocity is back the other way. And I curl with the field. And now the force is upwards. All right. So that's obviously something to hang on to. Note that F is perpendicular to V. And I'll maybe put a B underneath this F, just so we know. It's always the magnetic force on a moving charge is always perpendicular to its velocity. So I'll throw in a nifty little thing here. That being the case, well, two nifty little things, I guess. That being the case, if I drew this perspective for you and you were in a 4A class, what would you say that force is called? It's the one that makes things go in a circle, pointed at the center. Oh yeah, good one. It's the centripetal. So this is a centripetal force. So magnetic forces are centripetal on moving charges, and therefore the magnetic force will do no work. Oh, I guess if I were going to say FB, I guess I should say does. It does no work. No work can be done by the magnetic force. I want you to think about that for a minute. Okay? I want you to think about that for a minute. The B field does no work. Okay. So here's what I want to do with this problem. Since the magnetic force is centripetal, then what I can say here in my force, so if I use just regular good old Newton's second here, and I say that this is the only force acting, so the sum of forces is the same as the magnetic force, I'm going to set that equal to MA. Right? But it's centripetal. So because it's centripetal, I'm going to set it equal to mv squared over r. Okay. So now, in this case, QVB, sine theta was equal to 1 at this point because the angle, if you noticed, the angle between the velocity and the magnetic field is 90 degrees. The velocity is that way, and the magnetic field is that way. So it's a 90-degree angle between the two. So sine theta is equal to 1 in this case. And this is where we'll start off, okay? We'll start off with sine theta as being 1. And that will go away fairly quickly. So one question then is, can we find the radius of the turn? The radius of the turn would be something like this, like that. And why, sure, why not? Why couldn't we find it? Well, yeah, I'm just going to pop the R up on this side and divide the QVB underneath the MV squared. And I'm going to get rid of one of those V's. So I'm just going to divide the QB underneath, really. It's just the momentum of the particle divided by QB is the radius of the of the orbit here, the radius. It happens to be known as the cyclotron radius. All right, this happens to be known as the cyclotron radius. Okay. So now, since I just told you that we were going to work with 90-degree angles for a while, what if instead of doing this, what if I shot it in from down here at some angle up like this? Well, then what would happen? Well, V that way and B this way. Oh, still a 90-degree angle. Oh, okay, good. So you have to kind of make sure you look at the full 3D picture here, okay? All right, so there's that. So then, so that's for a moving charge, kind of an isolated moving charge. What would be good then is to go back to this idea that in a current, there is a moving charge. Albeit very slow moving charges, right? But 0.1 millimeters per second, as we found out, but they are moving, so that causes a field, all right? So let's take a look at electric current and see what we can figure out here. Boop, okay. Now, here's a current I. If I want to find out, for example, what the force is if I take a current, okay, and I do the same thing. If I want to find out what the force is on a current, right? Suppose that I take a magnetic field. I'll just do the same thing as I did up there, right? I shot in an isolated ion, right? Kind of like we did with the electron gun, except it would have been a positive ion gun. So suppose now I do the same thing, and I'm going to put this electric current in a magnetic field like this. Okay, there's a magnetic field, my horseshoe magnet, right? I've got the North Pole just behind the screen, and the South Pole is over here where we are. And I'm going to ask what happens to this. I guess I don't need to be putting quite so many dots here. So here's my B field. What happens to the wire as I turn the current on, say, right? So this is where it's helpful that we were thinking about positive charges as the flow of current, because now at least we don't have to think about something different for the right-hand rule. So because the current is flowing to the right, therefore the velocity of positive charges is to the right. And if you did a V cross B on this thing, you would have again ended up with something pointed downwards, right? So the force on this wire is going to be pointed downwards. And what you'll typically find is that when you do this, you have a wire and you put a magnetic field around it. And because it's a wire and it has to contain the charges, it's a solid object. It can't just move the charges and off they go. It's going to, right? It's going to kind of ding, it's going to click, but it won't just keep traveling. It'll stop at some point. So there'll be a force on this wire in the same way as we had the QVB force. Okay, so we'll go back to QVB here. QV cross B. Now, in this case, what I want to think about is how much extent of the magnetic field was there. So let's call that distance L. And I want to think of the charges that are moving past in the wire. So what I'm going to do is I'm going to, for right now, I'm going to say, suppose that I take V as some L. Actually, I guess I should make L a vector because V is a vector. So I'm gonna do this. Okay, I'm going to define L as that vector, so I can just do this. L divided by some time interval crossed with B. Right? So I see I haven't changed the problem. I've just changed what V is. Right? It's L in whatever time it takes the things to go through L. But since this is a multiplication and I'm interested more in the current than I am in any one specific charge, I'm just going to take this T here and I'm going to flop it underneath the Q. Since it's a product, I can do that. So now I'm just going to have Q in how much charge in delta T times L cross B. And charge in a certain amount of time, well, that would be the current, right? So this really is the current L cross B. IL cross B is the current electrical current form of the QVB law. So it still works, you just gotta look at it slightly differently by putting the dependencies elsewhere. All right. So this works well enough for an electric current. And what we would typically want to do here is to define the L vector in the direction of I. Okay, so if I, in this case, as it was going to the right, so I'm going to define my L vector as being parallel with that to the right. All right, so that's the current form of the Lorentz force law. Okay, so now that we've got that, let's do another example. Let's do this. Oops, what did I just do? Okay, I didn't do anything. Wonderful. Okay, so let's do an example. You know, every time I go to the airport, I have to carry this heavy suitcase. Well, gosh, nowadays they have them on little rollers. Well, back in my day, let me tell you something. We had to carry our own suitcases, and they weighed 40,000 pounds. It's a lot for a 7-year-old, but we did it. Well, suppose that I want to suspend a mass. All right. So suppose I'm going to suspend a mass, and what I want to do is I want to take a region of magnetic field, kind of like, let's say I've got a region of magnetic. It's got to be in red. Let's say I've got a region of magnetic field here. Okay, something about like this. Say, all right, this is my B field. B is all in here. Okay, and let's suppose that it's pointed. Let's suppose it's pointed in. All right. So B is pointed in. So now what I'm going to do is I'm going to take I'm going to take some copper wire and I'm going to form it into a loop. Okay, and I'm going to drive current through there. Well, I guess I'll put a battery in here somewhere. But what I want to do is hang a mass from this loop, and I want to drive enough current through the loop so that it suspends the mass. Why do I want to do that? Because I said I don't want to carry my own suitcase. I just want to have a little B field, and I want to put a current loop through the handle of my suitcase, and then I'm just going to have a battery running current through the loop, and I'll have a magnetic field there. All I got to do is carry the battery in the magnetic field. Much easier than carrying a suitcase. Well, we'll see. All right, so check this out. Let's suppose that we have some distance A here. Well, why would you do it there? Let's put it down here, A. Okay, so it's a rectangle of side length A. Although that looks like a G. Okay, no, it doesn't. So the question here is, we want to suspend the weight, the mass. I want to drive current around the loop. Okay. So why do I want to do that? Well, take a look. A current in a magnetic field will cause a force. So first question is, which direction should the current be going? And second question is, how big should the current be? Okay. Well, if I draw a force diagram, see, these things never go away. So if I draw a force diagram of the mass, okay, the mass, there's the mass, and it's going to have some weight. Okay. And I want to balance it. I want to suspend it upwards with a force due to the current in a magnetic field, ILB. Well, in this case, it'll be IAB. So let's do that instead. Okay, because that's the A is the dimension of the loop that is immersed in the magnetic field. Okay. And since the current and the, well, I skipped a little bit there. So since the current and the B field are mutually perpendicular, I don't need to worry about the cross product. All right, so good times there. So first of all, which direction is I going to be in order to cause a force upwards? Right, well, I need a force upwards. So what I probably should do is put my fingers. So what's the rule here? I look at IL cross B at the top left here. I go, all right, I want my force to be upwards, so thumb upwards, and I know B was inwards. Therefore, I must be going left to right. So let's make sure of that. Fingers in the direction of left to right, curl with the direction of B, thumb points force. So IL, B, force. Okay. As I said, there are at least 3 or 4 different ways of doing this. You can certainly also just have your XYZ axes pointed around like this. You just got to remember which one's which. Freeze. FBI. Sorry about that. It's an old physics joke. FBI. All right, never mind. So the current should be going around oops, the current should be going around in a clockwise manner. So current, that's the current direction. And from here, if I just want to suspend that mass, then fairly straightforward to then make a force balance and say that IAB upwards is equal to mg downwards. And so therefore I is equal to mg divided by AB. So that's not a big deal. This was really just about getting the force, getting the current direction. So you see there's a right-hand rule, which is straightforward to follow if you know A cross B, but what if you know C equals A? What direction is B to make C, right? So you have to kind of be fluent with the right-hand rule and be able to use it given two things and trying to look for the third one. All right. Okay. All right, good. So let's stop there. I think that's a pretty good set for now, and we'll pick up in the next one. We'll talk a little bit more about some trajectories and charge particles, and then we'll go into so this is mostly about forces of magnetic fields on current loops and charged and moving charges. So we'll go into a little bit more of trajectory, and then in the next video, we'll also do torque on current loops, and then we'll get out of that and go into sources of the B field, and that's going to be some good, clean fun. So till then, folks.